Hi there, everybody. In this section, we're going to look at implicit differentiation, which is a type of calculus that allows us to find derivatives of functions that can't be written in the way we're used to seeing functions. So it's a nice trick, and we use it a lot this semester. And it uses the chain rule, so this is a good time to learn it. So what we've seen so far is functions that are written explicitly in terms of another variable. So here we have y completely determined by x. Over here we have s completely determined by t. But some functions are defined implicitly, and it's defined as a relation. So a relation is just any graph or any set of points that can be graphed. It doesn't have to pass a vertical line test or anything like that. So here we have a circle, right? A circle is commonly used as, it's an equation, but it's not a function. Well, we're calling it a function because we could break a circle up into two different parts, right? Like a top half and bottom half. Each one individually is a function. So when we define a function, we're basically saying if it can be broken up into smaller bits, and those smaller bits are functions, then we can reassemble everything and it stays a function even after we reassemble it. A little bit different than what you may have learned in algebra class or something. But in calculus, we're mostly concerned with tangent lines at this stage. So we don't want to say, oh, it's not a function, so we can't find a tangent line, right? That's silly. If you look at this circle, there's tangent lines all over the place. And even over here, this odd-looking shape, you can see that every point has a tangent line. Maybe not in the middle, but all the other points have tangent lines, right? So we want to come up with a way of finding tangent lines or slopes of tangent lines without having to break up these implicit equations into explicit functions. And so what that means is that if f, so f is just a function, if it's described by this mess here, right? This is that four-leaf clover thing we saw before. It just means that if we write y equals f of x, that it's true for all values x in the domain. So it just means the graph, the points on the graph, satisfy that function and make it a true statement. Okay? This has nothing to do with the vertical line test or any of that stuff. Okay, so it's not even defined the same way. If we want to find vertical tangents, we're going to be able to do that, right? In fact, we already saw how to do vertical tangents earlier in the class. So it turns out we don't need to solve for f in order to find f prime. We're going to use implicit differentiation. And it's actually a really easy technique. It looks hard because these formulas look really weird and you haven't seen anything like this before. But it's actually an easy technique. So there's only three parts to it. Basically, you take your original equation, you don't manipulate or move it around, you just take the derivative of both sides. Anytime you see a y, think of it as y equals f of x. Don't think of it as like the variable y. Think of it as a function of, like, y is a function of x. And so when you take the derivative of y, the chain rule goes into effect because y is a function of x. So the derivative of y is f prime of x. So y prime of x is f prime. Right? It's just a function. We're using the same concepts we had earlier, but because we're using this simpler derivative method, we just have to remember about the chain rule. So when we use the chain rule, we just tack on a factor of dy dx or y prime, whichever one is fine, doesn't matter. And then we solve for dy dx or y prime because those are our derivatives. So take a derivative on both sides. Don't forget the chain rule. Tack on y prime. Solve for y prime. And that's it. So let's see what this looks like in a problem. So if we want to find the tangent line to that circle at the point 3, 4, so you can imagine what it might look like, right? It's going to be a line, straight line cutting through, tangent at that point. So there's no reason to go through all the trouble of solving that equation for y and getting the plus or minus and all that stuff. There's no reason to do it. What we do, just start with your equation of your circle, and implicit differentiation says we take the derivative of both sides. So what happens when we do that? Well, the derivative of x, remember we have this plus here, so the sum rule kicks in. So we're allowed to distribute this through the sum. You don't have to show that step. So the derivative of x squared is 2x. So this derivative is going to be 2x. What about this? Is it going to be 2y? Well, it turns out that, remember, y is a function of x. So when we take that derivative, we get a 2y times y prime. Because y itself is a function. It's not a coordinate. The way x is like a coordinate, y is not a coordinate. It's a function. And so don't forget that the chain rule includes this factor. And of course, this derivative over here is just 0, right? Derivative of a constant is 0. Solve for dy dx. So now we have the slope of every point around a circle. So the slope of the tangent line at every point around a circle is just negative x over y. Well, we have a point. Our point is 3/4, so we plug it in. So the slope is negative 3/4. Use point slope form. So we have x1, y1, and negative 3/4. Plug everything in and simplify and solve. And you can check your answer by making a graph. Really easy stuff. So that's a pretty easy one. Most of the homework looks like this. Set up your equation. Take the derivative of both sides. Don't forget your dy dx. Solve for dy dx. Plug in any points if necessary, and find the tangent line. So this is pretty much the most basic kind of problem. And again, most of your homework does look like this. But some of your homework looks more like the next problem, which is a little more complicated. So here we have a shape called a lemniscate. And it's a funny looking equation. And we want to know where on the graph is the tangent horizontal. We can see that there's going to be 4 horizontal tangents, right? Right here, 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 and here. So how do we possibly find the coordinates of these points? Well, we use implicit differentiation. And then we're going to come back and do part B. So part B is a different question. What happens here at the middle if we try to find the derivative? Are we going to get 2 different derivatives? Are we going to get that the derivative does not exist? Are we going to get 4 different derivatives? Who knows? So we're going to treat that center point as a separate problem. Okay, so we start with implicit differentiation. So here I use the prime notation. Instead of the ddx, I just use the primes. Now, you might just be tempted just to start ripping through the derivatives, and that's fine. But let me caution you about something. This, when you take this derivative, you're going to get a 2x here, and you're going to get a 2y prime. We kind of saw something just like in the previous problem, right? You might think the same thing's going on here. Just easy stuff. But there's actually a chain rule inside a chain rule here. This is a triple chain rule, sorry, double chain rule, whether it looks like one or not. So what you should do is always do the outermost chain rule first. So here we have a double chain rule, here we have a single. So I'm just going to do the double as the first step. I'm going to leave this one alone. You'll see why when I do the next step. Okay, so here, this outside function is just u squared, right? So u has its own chain rule, right? I need to multiply by the derivative of the inside, just like the chain rule says I do. So this 2 comes down, I put it here. This 2 here is this one, okay? I know it doesn't matter which one's which, but if you're doing problems and one's a 3 and one's a 4, this is the way I would do it. I would keep the chain rule stuff together. Don't pull it all the way to the front. Keep it with its chain rule stuff, like the whole thing's in parentheses, right? Because PEMDAS says that this 2 is closer to this than this 2, right? Parentheses, then exponents. So when you bring this 2 down, I'm keeping it closer, just so I remember which one's which. Now, I've done the outsidemost function. Now I'm going to do sort of the middle function, right? This has a chain rule. This has a chain rule, right? So the inside function comes with its own y prime, right? So here the derivative is 2x. Here the derivative is 2y times y prime, because y is a function of x. I combine these 2's together. I kind of simplify as I go with like numbers and stuff. Things like negatives and numbers, you can keep pulling them to the front and keep simplifying them. It never hurts to simplify numbers. And then here, same thing with this derivative, right? Derivative of x squared is 2x. Derivative of 2y is 2y. Sorry, derivative of y squared is 2y prime. Now what do we do? Well, we have 2 y primes. So I'm going to distribute this right side. This is just this foiled. Okay? Just a big old foil. Next step, what I'm going to do is I canceled this 4, this 2, and this 2. So I actually factored out a 2 and canceled, just because I want to keep simplifying it as I go. Then everything that has a y prime in it, I pulled it all the way to the left. Everything without a y prime, I pulled it all the way to the right. So this is, now we're just doing algebra, right? We did 2 steps of calculus, right? We did take a derivative and then chain rule, right? Everything else is algebra from here. And you can see that, you know, when you FOIL this, that you get a y prime here and you get a y prime here, right? So we get 2 y primes on the right, 1 on the left. So just rearrange it, then factor out y prime. So this is all just, I'm not showing the algebra, you guys can handle that. Simplify, rearrange, factor out y prime. So there down on the left, I just pulled out a y prime, and then I divide by everything else to solve for y prime. So this big, ugly monster at the bottom is the answer for the derivative. So what this is saying is that the slope of the tangent line at every point on that shape is a function of both the x-coordinate and the y-coordinate. So we found the slope without finding a closed form for the function. Like, we can't write this f of x equals blah, 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 or y equals blah, blah, blah. But we can write it as y prime equals something. So that's a really interesting trick, and it allows us to find slopes of really, really complicated functions, like this one. Now, the original question said, where are the tangents horizontal? So we saw a problem in an earlier slideshow, an earlier video, where we had a problem just like this. Well, you just set the numerator of y prime equal to 0, right? So that's just a mathematical fact. You're allowed to keep the denominator around, but it's not going to do anything. So you might as well just ignore it. So I just took the numerator of y prime that we got on the previous slide, set it equal to 0. Now, those of you who are really good at algebra and arithmetic, you're looking at this thing and saying, you can't solve this, we're stuck. Well, yes and no. We can't solve it, but we can factor it, and that's important. There is an x term in every, there's an x factor in every term, so let's factor that x out. So we have two things multiplied together that equal 0. That means that one or both of those things have to be true, right? So if you just had like x times y equals 0, x could be 0, y could be 0, or both. So we just have to solve these things separately. So we're going to look at the points where 4x squared plus 4y squared minus 1 equals 0, or just x equals 0, right? So either this has to be 0 or this has to be 0. We're going to treat this one in part B. I already took that as a separate thing, so we're just going to look at this. I already separated this out, so we're going to look at this one. What the heck does this mean? Well, let's see what we can do with this, right? Well, you see an x squared and a y squared, so you might think, maybe I can write this as a circle. You can. So look at what's going on here. This is actually pretty wacky. So this is saying every point on the lemniscate that is also on this circle has a horizontal tangent. That's pretty wacky, right? So we have to find the intersection of this equation and the original function. So all we have to do is back substitute and solve and see what happens. Okay? So we put this x squared plus y squared back into the original lemniscate. So remember what the original function looked like. It looked like this, and then it had 2 times x squared plus y squared squared. Well, if x squared plus y squared is just 1/4, we just put a 4th in there. Right? So I'm back substituting this whole thing into the original equation. This is a very common tactic. When you guys are doing the homework, if you get stuck and you have 2 equations that don't look like they have anything in common, or you just can't move any further, try taking one equation and putting it back into one of the other ones, especially the original equation. Simplify that expression, and it just, every time you simplify it, it tells you a little bit more. So this tells us x squared minus y squared equals 1/8. So now we have 2 equations that need to be true simultaneously, right? So even though when we plugged in this into the original lemniscate, it didn't solve the equation, but it reduced it to something easier. So now we have x squared minus y squared equals 1/8, and x squared plus y squared equals 1/4. This is enough information to solve the problem. It turns out you can solve these just by substituting, or if you prefer, just use elimination. It might be easier, right? Just add down, right? And you get x equals plus or minus 3, radical 3/4, and y equals plus or minus 1/4. So pretty interesting stuff. Yep, did that right. Now, you don't want to write it like this, especially on the homework. The homework is going to require you to write it out as a set of points. Follow the instructions on the homework for how it wants you to do it. On a test, I don't care how you write it. Okay? It might say biggest number to smallest number to biggest number. Whatever it says, follow the instructions. So how do we know those are the right points? Well, you can plot those on the original graph. I did this in Desmos. It's a really nice graphing tool, and got these really nice points. And you can see clearly that that is, in fact, where the tangents are horizontal. So I know we've only finished part A. That was part A of this problem. I know it's kind of a beast. That's sort of the way some of calculus is, right? For those of you moving on to other math classes, I'm sure you expect that those classes are beasts as well. But I just hope that everything up to this point made sense, even though it might be something you've never seen before. Right? I hope that it makes sense to you. Right? Okay, so let's keep going. Let's do part B. What's going on here where x equals 0? Let's find out. So let's see if the equation of the original lemniscate gives us enough information. So we plug in x equals 0. When you plug that into the original equation, you get this horrible thing, right? 2y to the 4th plus y squared equals 0. So I simplified this. This is not a direct substitution. I plugged it in, rearranged it, made it look nice because I want to factor it. Well, I can factor out a y squared. What does that do? Well, it turns out not much, because the only solution to this equation is y equals 0. So when we plug that into the derivative equation, you get 0 divided by 0, which is horrible. Well, that we know that does not exist, right? The only way we could solve this is by making a table and this kind of stuff. But this still should match what we think is going on. The graph has two crossing parts of the graph. So at 0, 0, we're getting an intersection. We know that a tangent line cannot exist at an intersection, right? In order to have a tangent line, you need to have a function, and it has to meet at one point. But, right, there's two different parts of the equation there, so it's a does not exist. So this is a nice way to prove algebraically what you thought was true to begin with. For those of you moving on to Calc 2, there is some stuff in Calc 2 that looks a lot like this, but you're going to use a different technique to solve it. But keep this in the back of your mind, because you don't use these more advanced techniques in this class very often. This is sort of a standalone thing. But for those of you moving on, you definitely will use stuff like this again. Okay, last example. So last thing we're going to do today is prove the power rule again using our newfound tool called implicit differentiation. So in section 2.3, we proved the formula for a whole number. And now we're going to prove that if n is a rational number p over q, so just a fraction in lowest terms, like 3/5 or 14/19, if p over q is a rational number, then the derivative is just p over q times x to the p over q minus 1. So here it is. So we start with y equals x to the p over q. So here we know y is a function of x, right? But we're still using implicit differentiation. You're allowed to use it to do any derivatives. It's more powerful than the things we've used before. Raise both sides to the power of q. So on the left side, you get y to the q. On the right side, it cancels the q. Use implicit differentiation. So think about what's going to happen here. Okay? On the right side, you're just going to get p times x to the p minus 1. On the left side, you're going to get qy to the q minus 1 times y prime because of the chain rule, right? Don't forget the chain rule. So notice we're not using the power rule that we already know. You guys might be thinking, wait a second, we already know that the power rule is true. Can't I just take the derivative here? We're basing this on the whole number rule that we proved in section 2.3. In order to develop a rigorous proof, we have to base it on rigorous mathematics that have been proven beyond the shadow of a doubt earlier in the class. So here we're just using the fact that p and q are whole numbers, right? And we've proved for whole numbers that this is true. And the chain rule proof, I know it's pretty out there, but the chain rule proof was given in the previous slideshow. I didn't do a video on it, but it was in the slideshow if you want to read it. So here we have all this stuff. And now we want to solve for y prime. So I'm just going to divide both sides by this thing, and you get that, right? So p divided by q is p over q. So what we need to look at is the x's, right? So we have p minus 1. When I divide by this, that's the same as multiplying by y to the negative, right? Because a negative exponent is 1 over. And then what we have to do is simplify these exponents. But you might look at it and go, yeah, but one is x, one is y. There's no way to simplify these. Well, this is where that bag substitution comes in. We're going to plug in y equals x to the pq right here. And then all you have to do is sort through the algebra. Okay, so you just distribute this. So you're going to have p over q times negative q, and p over q times negative negative 1, which is 1. So we're going to get negative p, right, over q, and then negative negative q minus 1, right? So all we're doing is we're just bringing it out and multiplying it. Nothing fancy is going on there, right? This is just the definition. Now we distribute, and then you arrange similar terms and cancel. So you can see here, this P and this P cancel. You get a -1 and a minus P over Q, so you get P over Q. And there you go. And that's the answer. So that's how you prove the power rule, the second part, using proven knowledge from earlier in the class. So highly recommend you make sure that you can go through this and do the arithmetic on your own. And we will prove the last part of the power rule in section 6.4. That takes a lot more fancy stuff. But by the end of the class, we will prove this rule that we use all the time. And that's it for the video. So there's some really great problems. Your homework isn't real long on this section. And you can probably whip through like the first few. If you remember the 3 rules early on in example 1, you can just pound through the first few examples, the first few homework problems. After that, some of the ones at the end are a little more intense. Take your time on those. And as always, if you have questions, email me or post a question in the discussion forum or jump in on one of the video sessions. So that's it for today. I will see you guys next video. Until then, bye-bye.